Okay, we also did, it's thinking, we also did this slide, okay? And this slide starts to kind of show you, we're going to talk more about the layers of the Earth's atmosphere, okay? Remember I started to draw over here, I said the troposphere. What's above the troposphere? Starts with letter S. Stratosphere, exactly. Into the stratosphere. Okay, so you kind of start, we're going to talk about layers of the Earth's atmosphere momentarily. Okay, this Kittinger jump up there, anybody familiar with the Kittinger jump? Anybody familiar with the Red Bull Stratus? Okay. Red Bull Stratus with Felix Baumgartner.
Yes.
Replaced this guy's record. Very high up there in actually the stratosphere. Okay. So one of the things, oh, by the way, we have a new student. We have another. Oh. And this actually is, well, you probably already found him. Yep, you're doing fine.
Right there.
Yep. So, so one of the things that differentiates, let's look at it this way. The troposphere, so here's the geosphere, and this is all the atmosphere. The thing that separates the troposphere from the stratosphere is what it does with regard to temperature. In the troposphere, as you go up, it gets cooler. And if you're like me, probably up to before I started teaching this class, I think, well, it just gets cooler as you go up in the Earth's atmosphere. Not true. As you go up in the stratosphere, actually it gets warmer. This figure is showing you that. This figure is a little different. Along the y-axis, we do have height. We're going up in elevation from the Earth's surface. Okay, but notice along the x-axis now we have temperature. So that kind of zigging and zagging thing is the zigging and zagging that the temperature does. Hi. Okay. So the way you read this is, if you were clear up here on Mount Everest, what do we think that the temperature would be?
Around -45.
Yep, I like that. I kind of jagged over. But I'm liking like -45 Celsius.
Yeah.
Yep. Or -50 Fahrenheit. Yeah, that's how you read that. What about if you're up here at about, let's see, what would this be? 25 miles? Okay, about 25 miles. What's the temperature here? Yeah, well, it's only a mild -20. Okay. -20 Celsius, isn't that weird? Or a little below zero Fahrenheit. So my point is, it gets, as you go up in elevation in the troposphere, it gets cooler. As you go up in elevation in the stratosphere, it gets warmer. And I have a slide coming up to say why that is. It gets warmer. So what did I say? There's good and there's bad, and the formula for it is O3. What is it? It's oxygen with 3 atoms stuck together. It's not oxide. It's ozone. Yep. Ozone. The ozone layer, I think I even mentioned, that's why I kind of put stratosphere on the board last week, is because the good ozone layer is actually here. And that's actually what makes that kind of temperature trend. So we're going to talk about above the stratosphere is the mesosphere, above the mesosphere is the thermosphere. We're going to talk a little bit about those. So this is where I get to say, don't do what I'm going to do. If you do a report and you use Wikipedia, you will get an F from any teacher that's worth his or her salt. But that said, I'm going to go to Wikipedia and show you what they have to say for the Red Bull jump. You know that happened. And did you see like videos of his mom going, oh my gosh? No, I just could not handle that if that was my son.
He was in the air for how, like 8 minutes?
I don't know. It was a long time.
No, he was at terminal velocity for 8 minutes. Excuse me.
He was in the air longer than that then.
Yeah, he was in the air for, I think, like 12 or 13 minutes then.
Look at this, might say it somewhere.
He
It was
jumping?
He
nobody.
jumped from, basically
Right.
from the edge of space.
Right, he was in the air going up.
up for like hours.
Yeah. I don't know how long it took him to get up there.
And did he do it 3, 4 attempts? I don't know.
I don't know how many times he did it.
I believe it was 3 jumps and each jump got higher.
That's crazy.
Yeah.
Is it the guy that landed on his feet too? Like he landed?
I don't know.
Oh, he
I think
landed.
I've watched it.
Yeah.
Did he?
When you're that good, you don't not let it.
Well, somebody made that a big deal, and I was like, well, it is kind of
There are guys who put like,
It's pretty cool.
like
Yeah.
We need a
targets.
YouTube.
There are
We need a
guys who
YouTube
put weight
says.
running around and literally stop.
Oh.
You don't need no facts, we just need to watch it.
I have a
Yeah, we should
YouTube
watch
video
it. I
of the
agree.
Kittinger jump, but,
Yeah, we
because
can
to me,
watch
when I
Kittinger
looked for
video.
YouTube videos, that was even more striking than the Felix Baumgartner jump. But I like this when it finally comes up, this Wikipedia. What's that?
The Baumgartner jump has awesome music in the background too.
But the thing about that with the previous jump though, think of the technology, Chief.
That's
true.
very
I mean,
true.
this dude was jumping in jeans and a t-shirt compared to this dude jumping in a...
legitimate NASA space.
I like that.
Yeah.
I like that. It's coming. So this is what I was waiting for. So let me know if you see flew approximately 30 knots. Well, that's not the time. That's the elevation. But one of the
Deployed
things.
his parachute after 4 minutes and 19 seconds.
The total jump lasted 10 minutes. Oh, that's terrible. It's terrible. I'm afraid of heights. I like this right here. This figure kind of summarizes the situation, I think. So we've been talking about the layers of the Earth's atmosphere. The troposphere is actually the thinnest. On top of the troposphere is the tropopause. Then it transitions into the stratosphere. That kind of purplish there is the ozone layer. So you can see Baumgartner, looks like he was 1, 2, 3. Wait, who's that guy? Who's Mr. Estes? I don't know. But here we got the, I'm going to have to look that up. Note to self. Just this last October. Because here is Felix's jumps, 3 jumps, and here is Kittinger's jumps. Back in, like you said, when he was wearing jeans and a t-shirt, 59,
Well,
60.
yeah. What was the name of that second guy you just asked about?
Eustace. Estes.
E-U-A-S-T-E?
No, I told you wrong. Eustace. 2 vowels.
Say that one more time, please.
EUSTACE.
Perfect.
Thank you. So, yeah, that was in October. I missed that one. That one wasn't that long ago.
Yeah, that guy was up there.
Yep. So, just to kind of get a sense for it. So what do you think? The troposphere is topped by the tropopause. So that puts Felix and this guy just barely in the stratosphere. Almost in the
Yeah, I think I might have been talking about
the other guy, yeah,
'cause
that happened
that wasn't
recently.
that long ago that I watched.
Yeah, we'll have to look into that one.
YouTube.
I know, it's all there. The thing about YouTube is sometimes there's too much there and I can't find exactly what I want.
Probably wearing a GoPro on his way down.
Yeah.
Was he really?
Yeah, the one
Probably
I
what?
watched
That'd be
him.
cool.
What about on his way down?
He's wearing a
A
GoPro.
GoPro, it's like a camera that you can put
You put it
anywhere.
like on kilometers or.
Oh, yeah.
They're super tough.
Yeah.
That's what I trust up there.
So just to kind of emphasize back to kind of the science of the atmosphere, the dry stuff. The troposphere actually is the layer that's closest to the Earth. Honestly, we're going to spend probably 98% talking about what's happening with this part of the atmosphere when we're talking about the atmosphere. One of the reasons is because the weather is basically confined to the troposphere. Okay, this is where nearly all, so I qualify it, of the weather occurs in the troposphere. Clouds are a lot that has to do with the weather, right? The whole hydrological cycle, the evaporation, condensation, precipitation. We do it all over again. Okay, if we have any sort of rotation, that's going to, wind, okay, that's all going to be affecting us in the troposphere. It is the thinnest. Here in a minute, I have a slide to show you that its height varies. Okay, so the height of the troposphere, we're going to see it's fluffiest near the equators, and it's kind of thinnest, the troposphere is thinnest near the poles. The reason we see this trend in temperature, the temperatures get cooler, is because this Earth, the geosphere, is an awesome little radiator. When the Earth is facing, when the part of the Earth that's facing the sun is facing the sun, that part of the Earth actually is sucking up about as many heat particles as it can. Am I going to fall?
You're gonna fall.
He's pointing out my shoelaces.
And you kept stepping on it. I was just waiting for you to fall place flat.
And then like a gentleman, you'd be like, oh. So one of the things I'm after with regard to the science of weather is, can you tell me and kind of get a sense for what are these layers, these horizontal layers we're talking about? We'll talk more about temperature inversions. They are a cool player that happen within the troposphere that bring us some interesting weather. In the meantime, did you find about?
Yeah, I did. Alan Estes. Trying to find the date.
October, it said something.
It said October 24th, 2014.
October 20, yeah.
It's like a Halloween jump.
He broke Baumgartner's record.
And we missed it.
Well, because he didn't have Red Bull back.
He didn't have a
Yeah.
sponsor. Well,
Did he
dang
have any
it.
sponsors at all, or did he just do it
Yeah,
himself?
he actually is, where did I
Track
find
that
it?
down.
He is an engineer for Google.
No, that should have gotten out there.
He probably had the money to
That's
pay
what I'm
himself.
saying.
He probably
That's
could,
not
he probably
fair.
gets paid enough by Google
Engineer
to pay
for
himself.
Google.
Very good.
Considering interns at Google get paid $60,000 a year salary.
Everyone wants, my daughter wants to work at Google. She's a chemie, so.
135,890 foot, and Baumgartner's was 128,000.
Dang, that's a lot.
Wow.
And he
25
survived his,
miles.
we'll have to look into that. We'll
That's
look for
kinda
that.
neat.
Well, I mean, I guess at that height, you got all the time in the world to pull the chute.
Yeah, I mean, you should
Oh,
find
you
it pretty
should-
good.
I think it's a timing thing, though. I don't know. I'm thinking, and if you pass out, that's
You
not
can't
going to
pull it
happen.
too soon.
Yeah, you're probably right.
I don't know. It's still scary as heck.
It's really cool,
But
though.
thank you, Wikipedia, right? Mr. Google himself probably made sure Wikipedia updated their little figure there. So,
In the upper layers of the stratosphere, temperatures increase with altitude, not decrease.
that's what we're
I'm
studying.
I'm just reading an article about it.
Yeah,
Saying
see,
that.
you're like, dang, I knew that. Or you might want to know it for a test, I don't know.
Really hot ones there.
But actually, this next topic, short topic, I want to talk about is how is we sending up weather balloons. Are you familiar with the concept of a weather balloon? Well, we are going to watch a short video on sending up a weather balloon because I think he does a good job. But the reason we send up a weather balloon is to get kind of a profile or a picture of this cooling temperature. Weather balloons go up, right? I think it's kind of a cool phenomenon. We're going to be talking more about this temperature profile because actually it's a player in whether you're going to have severe weather or not. How rapidly or how slowly within the troposphere those temperatures are cooling gives you severe weather or not. So this temperature of cooling, this cooling rate, actually we call that the ELR. The top of this slide, if you want to put ELR next to environmental lapse rate, you can. We're going to return to this when we start to talk about clouds. Environmental lapse rate. And in general, if each of these notches is 1,000 meters or 1 kilometer, in general, the temperature cools 6.5 degrees Celsius for each step you go up, okay? So if it's, let's start with something easy. If it's 0 Celsius, okay, if you go up 2 kilometers, what temperature will it be cooled down to if it's cooling at 6.5 for every kilometer? 6.5 times 2, right? So 13. It'd be negative 13 kilometers, or excuse me, negative 13 degrees Celsius. But that's just a general environmental lapse rate. So it's so important that in order to get the real deal of what the temperature's doing as you go up in the troposphere, they send up weather balloons. So here is, so I mentioned that the troposphere actually is thickest, where is the thickest? At the tropics, the equator, very good, and that's all this is saying. So what's on top of the troposphere as you go into the stratosphere? The tropopause, exactly. Okay, so basically it's saying that the top of the troposphere, where the tropopause is, at the equator is like that. Okay, at the poles, it's like this. Okay, so it gets thinner there. So a lot about the troposphere. The next one that's got some substance to it on my slides anyway is the stratosphere. So the stratosphere, like I said, has the good ozone layer, okay? And actually, it's the presence of this good ozone that this O3 here is great at taking in sun's energy, basically, and oozing it, radiating it away. So actually, it's another little heater, kind of like the geosphere was a heater, so is the good ozone. Yeah. Then I don't have a whole lot to say about the next two layers. And actually, I'm going to introduce a fifth layer. But above the stratosphere is the mesosphere, and it's even wider than the stratosphere. And above the stratosphere is the thermosphere. So these aren't necessarily drawn to scale, okay? So this is the meso, meaning middle, sphere. The thing about the mesosphere is it's like the troposphere with regard to temperature change. So as you go up in the mesosphere, again, it gets cooler. And you can see that on that figure, that kind of zigzag. And then we get to the thermosphere, where I'm just going to kind of draw dots up here. Okay. Your book will tell you it's about sparsity. Because we said that air gets thinner as you climb a mountain. So what do you think the air does as you leave the troposphere through the stratosphere, the mesosphere? Up here, basically, you're talking about gas particles that are, so, you know, gravity is holding them to the earth, but it's just kind of like, oh, not very much. So the thermosphere, if we kind of finish this trend of does it get warmer or cooler, actually, if you look back at that figure, within the thermosphere, it's kind of like in the stratosphere because it alternates. But here's the thing about the temperature. At some point, you are in outer space. Actually, that's why I wore this t-shirt today. I knew we were going to cover this topic. So basically, it says weather forecast for, I think it says outer space or something like that. Okay. Forecasted low, forecasted high, both on the Celsius scale, -270. And if you're familiar with absolute zero, the concept of absolute zero, we'll talk a little more about temperature scales, but absolute zero is 0 Kelvin on the Kelvin scale. Absolute zero is -273 on the Celsius scale. So it's within 3 degrees of absolute zero is what this is saying. My point is in outer space is a kind of whole other cat. If you Google what is the temperature in outer space, which I've done not that long ago, you get them talking about, well, in order for something to have a temperature, it needs to have matter. It needs to have atoms, or atoms connected together to make molecules. In order for something to have a temperature, it needs to basically have mass and occupy space. In outer space, it's mostly vacuum. So that makes it a little problematic. And then aside from that comes well, what is your vicinity to a star? And of course, the sun is a star. So I've also read, and this reminds me of kind of that movie Gravity, right? I don't know if they did this in the movie, but if you're facing the sun, you know, and you're not wearing a suit that will help kind of acclimate your temperatures, okay, you're going to be hot where you're facing the sun, and on your back you're going to be just freezing cold. It's kind of the way the radiation will handle you.
No, that whole entire movie was just like,
Ooh, what's that?
That whole entire movie, Gravity, none of that. It was just her sitting in space.
I've heard Neil deGrasse Tyson really rip on that movie Gravity, you know, and I can't blame him. I liked it.
Really?
It's very far-fetched, but I liked it. I liked
Interstellar
the,
was great.
yeah.
Interstellar was awesome.
I like Firefly.
I don't think I've seen that yet.
I like Deep Space. Inner Space.
You like what?
Inner Space.
A movie, Inner Space? don't think I've seen that one either. Okay. Well, maybe I have seen it then.
I actually enjoyed it.
Okay.
It's a good movie though.
Okay.
Space
I think we're okay with, I'm not gonna show you this. I am gonna see if we can see next time a video of that one dude, the latest dude. Okay. But I wanted to talk about this other layer, okay, called the ionosphere. And in the other physical science I teach in the fall is astronomy. So in astronomy, we talk a little bit about the Van Allen belts, the Van Allen radiation belts. I don't know if anybody, the dude who found them actually is from Mount Pleasant, really big hairy deal. Yeah. Anyway, those radiation belts, if you're familiar with them, actually are kind of embedded in this ionosphere. Ionosphere is when it gets overloaded with charged particles from the sun, that's when we get our northern lights. Anybody in here seen northern lights? We talked about that, didn't we? I haven't yet really seen good northern lights. It's on my bucket list. So like this next slide, I think says, the way the ionosphere gives us our northern lights is this. And actually we are going to talk about the sun's activity. Sometimes the sun is really relaxed with no sunspots, no solar flares, no coronal mass ejections. And then sometimes that sun is just off the wall. Right now it's kind of more off the wall. Okay, so if it gives us too many charged particles, the ionosphere and or those radiation belts cannot hold all that. They have a capacity. And so when they leak, they are going to leak at the poles. The magnetic poles, okay, there's the poles that the Earth spins on, okay, the Earth's rotational poles, and then there's the magnetic poles. And right now they're close, okay. Of course, there's that movie about the poles flipping, which actually the poles have flipped, and the poles may be due to flip, which is another interesting thing, right? But, what's that? But anyway, so the up here we're a little sensitive to actually those charged particles falling through if the ionosphere can't hold them all. Okay, so last slide, last but not least. One other sort of more general way than these 4 layers of the Earth's atmosphere and throw in the 5th layer of the ionosphere is to talk about the homosphere and the heterosphere. So if something's homogeneous, how would you describe it?
Same mixture.
It's the same, it's mixed really good, yep. So what we find is actually near the Earth's surface, okay, we kind of have a nice mix, okay. They're in about, beginning with, at the end of the mesosphere, so actually on top of the mesosphere, there's, guess what, a mesopause. So beyond the mesopause into the thermosphere, we start to kind of get this layering by mass. The heaviest stuff, nitrogen, followed by oxygen, followed by helium, followed by hydrogen. So, in my other class, somebody said, so is it flammable up there? I'm like, I don't think so. I think you need hydrogen and oxygen really to flame. But it's an interesting question. So if you guys are okay with it, I know it's early, but let's go ahead and take a 10-minute break now. And then when we come back, we're going to start with next chapter. That'll give you time to go print it off if you haven't. So,
Oh, yeah.
you know how to print it off and everything.
Yeah, I'm sure I'll find it.
Okay.